Alright, so for this activity, you are to determine the acceleration of a cart as it goes down the inclined plane. Hopefully you collected at least 5 datum, and you created a position time graph. We use the word position here and assume that down the inclined plane is the positive direction. And hopefully your 5 data points sort of begin to look like this. Now that is not a straight line. That's definitely a curve. So there's not a best fit straight line here, but we could draw a best fit smooth curve, or we could pass through as many of them as possible. Now this shows me that in every time interval the position change was increasing. So that means that the slope of this line was changing. I want to find the speed or the velocity of the object at any time. I would have to find the slope of a tangent. So imagine a tangent line at the beginning. Now our tangent line is going to change. I'm drawing some little red tangent lines here. So tangent, tangent, tangent. Notice that the slope of that tangent line is changing. And if the rate at which that change is occurring is constant, then we have a changing velocity. Now, the slope of this little chord there would be the average velocity. The average symbol is a straight line across. So we can find the average velocity for line segments between each one of the data points here. And once we get those averages, you could then create a velocity time graph, an average velocity time graph. Now the important thing to remember here is that the average velocity occurs midway between the time interval. So if you're looking at a 1 second time interval, the average velocity occurred at half a second. If you're looking at the time interval 1 to 2 seconds, the average velocity occurred at 1.5 seconds. So if I've got my beginning and ending there, my average velocity is going to occur midway between those two times. So I could graph that on my velocity time graph. Using the midtimes. So this would be my V1, V2, average velocity 3, 4, there we go. So if these all line up, they look pretty good, like they're on a straight line there. You can draw a best fit straight line through those average velocities. Now just like before with the distance time graph or the position time graph, we can write an equation for this line. If you use the basic y equals mx plus b, and make a substitution of those values, those quantities, excuse me, then y equals the slope of the line, x plus b. In our case, y is the average velocity, the slope, some value, x is the time. And most likely, your intercept here would be 0. May not be perfect from your lab. And if it's not, then that would be your initial velocity. So it may be that your object is starting, or the time starts and the object is already moving. So let's discuss the slope. Slope is rise over run. So it would be our change in average velocity over change in time. And we can make a equation for that. So the slope is delta V over delta T. The units would be meters per second over seconds, which is also known as meters per second squared. This quantity is known as the acceleration. Acceleration is the rate at which the velocity is changing. It is a vector. It has magnitude and direction. And it's the slope of a velocity time graph. Remember, velocity is a vector. So when you take a vector and you divide it by time, which is a scalar, then you get a different size vector. So our acceleration is a vector. That means a positive acceleration is important. That means a negative sign on an acceleration is also important. And remember, a vector has magnitude and direction. And magnitude is just a fancy way to say amount. It's the number. It's the value.